Now we need to calculate combustion reaction for next mixture. We have mixture between propane and butane, and volume of this mixture 100 liters. Mass fraction of propane 70%. This mixture measured, then pressure equal 750 millimeters per mercury, and temperature 20 degrees Celsius. So we need to calculate heat effect for combustion reaction. To calculate heat effect of all reaction, we need to sum heat effect of combustion reaction for propane and butane. How we need to calculate exactly these heat effects? We need to know numbers of moles for first gas and standard heat of formation for this gas, and the same situation for second gas, numbers of moles for butane and standard heat of combustion for this gas and butane. To calculate numbers of moles, we need to use normal conditions and joint law of gases. Well, we remember that numbers of moles, it's a volume of gas over molar volume. But to calculate volume, it's better to write volume with index 0, because we need to calculate it in normal conditions. So, you remember joint gas law, PV over T0 is PV over T. In this situation, so volume in normal conditions, it's a pressure in our room condition, in our task, multiplied volume in our task, temperature in normal conditions, and over temperature in task, and pressure in normal conditions. So what we have, 750 multiplied volume 100 liters, temperature 273, and over temperature. In our situation, we need to write in kelvins, so 293, and pressure, atmospheric pressure, 760. And it gives us 92 liters. Now let's calculate volume of exact gas. Volume of propane equal mass fraction of this gas multiplied volume of all mixture. It equal 0.7 multiplied 92 liters, and it equal 64.4 liters. The same situation with volume of butane, or it's different between volume of mixture and first gas. Volume of mixture minus volume of propane, 92 minus 46.4, and it gives us 27.6 liters. Now let's calculate numbers of moles for both gases. So for propane, volume over molar volume, and it equal 64 0.4. Molar volume of all gases and vapors in normal conditions, 22.4 liters. So here we have approximately 2.9 moles. And for next gas, the same situation, the same formula, same ratio, but now we divide 26.6 over 22.4, and it gives us approximately 1.23 moles. And finally, we can calculate heat effect of combustion reaction. As I already said, the numbers of moles for propane multiplied standard heat of combustion for propane plus numbers of moles for second gas multiplied standard heat of formation for butane. And according to table data, we'll take the standard heat of combustion for both gases. And what we have, 2.9 moles for propane, multiplied minus 2,220 kilojoules per 1 mole in the standard heat of combustion for propane, and sum of 1.23 moles for butane, and standard heat of combustion for this gas minus 2,877.13. And finally, we have minus 9,977 kilojoules. One note that for standard heat of formation, standard heat of combustion, units is kilojoules per 1 mole. But here we're using calculation exact amount of substances. So heat effect, unit for heat effect of all reaction, just kilojoules. Next task, we need to calculate heat effect of iron reduction reaction according to following equation. Iron oxide in solid form plus hydrogen in gaseous form give us pure iron, as well solid form because it's metal, and water, but here in gaseous form, so water vapors. And we need to calculate heat effect of this reaction. But what given exactly in this task? We know heat effect for following reactions. First reaction, iron oxide react with carbon monoxide, and it gives us pure iron plus CO2, and heat effect for this reaction minus 18.2 kilojoules. Next reaction, 2CO, so we have combustion reaction, give us 2CO2, and heat effect of this reaction minus 566 kilojoules, and it's given standard heat of formation of water. Let's write this reaction between hydrogen and oxygen, and it produces water vapor. But we remember that standard heat of formation is a heat which we need to produce just 1 mole of complicated substance from simple substances, and according to this thermochemical equation we can use fractional odds. So we need to write here just half of mole for oxygen. Well, and standard heat of formation for water vapor according to table data, equal minus 241.8 kilojoules per 1 mole. And what we can do in this situation, how we can solve this problem, to calculate heat effect of first reaction, knowing heat effects of these three reactions. As you remember, I said that for thermochemical equation, we can use different mathematical operations. So we can sum these reactions, we can subtract, we can multiply it or divide on any numbers. So here we can use Hess law and we can use different mathematical operations. What we can do? As you look in this first reaction, we don't need carbon oxides, so we need to cross CO and CO2, and oxygen as well. Let's do this. Let's divide second reaction on 2 and do these operations. We subtract second reaction from first reaction, but sum last reaction. Let's do it. Well, what we have in this situation. So, first equation we don't need to change, so we rewrite it. Iron oxide in solid form plus CO. Then, second reaction, they said what we divide by 2, and we have CO once again, minus half of mole for oxygen. And third equation, the same, we don't need to change it, just sum with previous equations. So, plus 1 mole of hydrogen and half of mole for oxygen. Now let's make the same algebraic operation with the right side of our equations. So we have pure iron in solid form, carbon dioxide in gaseous form. Second equation, you remember what we subtract, so we have CO2 once again, and plus 1 molecule of pure water in gaseous form. And we see that we can cross carbon monoxide, we can cross pure oxygen and carbon dioxide. And finally, after this algebraic operation, we see that we get initial equation which we need. So, iron oxide reacts with pure hydrogen and produce pure iron and water vapor. Well, but how to calculate heat effect of this reaction? In this situation, we can make the same algebraic operations which we made for equations. So, heat effect of all reaction will be heat effect of first reaction, then we subtract second reaction and we divide second reaction by 2, so minus half of heat effect for second reaction and plus standard heat of formation for water vapor. And what we have? Heat effect of this reaction equal minus 18.2, it's a heat effect for first reaction, then minus half of heat effect for second reaction equal 566, and we need to sum standard heat of formation for water, minus 241.8 kilojoules per 1 mole, and it gives us 23 kilojoules. In next task, we need to calculate heat effect for following reaction between two oxides. Aluminium oxide, aluminium 2O3, and sulfur oxide, 3SO2. First in solid form, a second substance in gaseous form, aluminium SO3. And of course, it produces salt. So we have aluminium 2, SO4, as well in solid form. And we need to calculate heat effect of this reaction, but in standard conditions. To solve this problem, we can use first consequence from Hess law. Because this reaction is formation reaction, we produce salt from two oxides, so we can calculate heat effect for this reaction as a difference between two sums. Firstly, we need to write standard heat of formation for product, delta FH 0 298, for salt, aluminium 2SO4. And then we need to subtract standard heat of formation for both oxides, but please remember that standard heat of formation is a heat that's given just for 1 mole substance. Here we see that reacts 3 moles of SO3, so we need to write it in our calculations. Well, minus standard heat of formation for aluminium oxide, aluminium 2O3, and minus 3 standard heat of formation for sulfur oxide. According to table data, thermodynamic data, we put numbers in our calculations. So for salt, standard heat of formation minus 3,439 kilojoules per 1 mole. Then for aluminium oxide, minus 1,672 kilojoules, and minus 3 standard heat of formation for sulfur oxide, and it equal minus 395.7 kilojoules for 1 mole. And in our calculations, we have the standard heat of this reaction minus 580.8 kilojoules. And as you see, of course, we have minus 588 kilojoules, so we can say that here we have exothermic reaction, where heat released. Now we need to calculate heat effect for reaction of esterification of oxalic acid with methyl alcohol. This reaction goes according to equation COOH doubles plus 2 moles of methyl alcohol, CH3OH, and give us ether, COOCH3 doubled plus 2 moles of water. This reaction is combustion reaction because I already said organic substances mostly participate in combustion reaction. So now we need to use second consequence from Hess law. So heat effect of the reaction in standard conditions. So you see this index for standard conditions. And this is the difference between products for standard heat of combustion of reactants and standard heat of combustion for products. So how we can calculate in this case heat effect of all reaction? We need to use standard heat of combustion for acid, COOH. Then we need to sum standard heat of combustion for alcohol, but once again, keep in mind that we need to use exact numbers of moles for our substance. So 2 standard heat of combustion for this alcohol, H3OH. And now we need substrate standard heat of combustion for products. But you remember that liquid water don't participate in combustion reaction, so standard heat of combustion for liquid water equals 0. So we need substrate standard heat of combustion for this organic substance, COOH3. Well, let's put here table data, thermodynamic conditions. So what we write here? Minus 251.8, then plus 2 multiplied minus 727.59 kilojoules per 1 mole. And now we substrate product minus 1680.19 kilojoules for 1 mole once again. But at the end we have minus 26.79 just pure kilojoules. So as you see, combustion reaction, I already said that combustion reactions are exothermic reaction, so minus 26.79 kilojoules. We need to calculate heat effect for following reaction. We have reaction between metal alcohol in gaseous form, oxygen in gaseous form as well. And of course it gives us carbon dioxide gaseous form and water vapor. But we need to calculate heat effect of this reaction not in standard condition like in previous calculation, but then temperature 500 kelvins. Well, what we can do in this situation? Of course, firstly we need to decide which consequence we use from Hess law, first or second one. Firstly, we can say, because we have reaction between organic substance and oxygen, we have combustion reaction, but combustion reaction we have actually when this reaction gives us not water vapor, but water in liquid form. So here we have formation reaction, and we need to use first consequence from Hess law. So we can calculate heat effect in standard condition, like difference between standard heat of formation for CO2 plus 2 standard heat of formation for water vapor minus standard heat of formation for organic substance CH3OH. And then you may think that we use standard heat formation for oxygen, but according to theoretical position, standard heat of formation for simple substances equals 0, so we don't need to write it. And using table data, thermodynamic data, let's put numbers in this equation, in this formula. Minus 394 plus 2 multiplied minus 241.8, and then minus 201.2 kilojoules per 1 mole. And in our calculation we have this reaction as well as the thermic reaction with release of heat, 676.4 kilojoules. But here we calculated a standard heat of formation in standard condition. In our task we have 500 kelvins, not 298 kelvins. What we can do, we can use Kirchhoff equation. And Kirchhoff equation, firstly we place in this equation standard heat of all reaction in standard condition heat effect, and we need to know this change of temperature. So we need to put integral from 298 to 500 delta Cp, where Cp is the molar isobaric heat capacity, and over dt. So heat effect for this reaction is a standard heat effect plus delta Cp delta T. Okay, now we know how to calculate heat effect in real conditions, not in standard, but then temperature 500 kelvins. But now we have one more problem, how to calculate change of molar isobaric heat capacity. We can do it easily. We can use first consequence from Hess law. The same situation, it will be difference between molar isobaric heat capacity for product. In our situation, there's carbon oxide and 2 molar isobaric heat capacity for water vapor. And then we use molar isobaric heat capacity for reactants. So, first reactant, molar isobaric heat capacity for alcohol, and then minus molar isobaric heat capacity, but taking into account numbers of moles, for oxygen. All molar isobaric heat capacities as well table data, so we need just take this data and place in our calculations. In this situation, we have 37.13 plus 2 multiplied 33.56 minus 43.9 and minus 3.5 multiplied 29.36, and it gives us 16.31 joules per Kelvin. Okay, and now we can easily put all these numbers in Kirchhoff equation and calculate heat effect under 500 kelvins. So once again, it will be heat effect in standard conditions plus delta Cp and multiplied on difference of temperature, 500 minus 298. So let's put numbers: minus 676.4 plus. But one note that heat effect we calculated in kilojoules. Change of heat capacity, molar isobaric heat capacity, joule per Kelvin. So we also need to use the same unit for different parameters. So let's write heat capacity in kilojoules. And it will be 16.31 multiplied 10 power to minus 3. And a difference in temperature, 202. So heat effect for this reaction will be minus 673.11 kilojoules.